So over the past 50 years or so, computing power has doubled every 18 months. And when you add that all up, it's really pretty amazing. The smartphone that I have in my pocket is more powerful than a supercomputer from 1970. So a natural question is, where does this ultimately lead? Do we run into some limit? Does this stop? Certainly there have been some signs lately of running into limits. Clock speeds, the number of computational operations per second that computers can do, actually stopped increasing about 10 years ago. And the feature sizes, it seems hard to shrink them much further because you can't really make them out of things that are smaller than an atom. So what happens next? You could try to find some kind of shortcuts. The big example of that is quantum computing. Prior to quantum computing, no one really ever found any shortcuts. The number of steps you needed to solve a problem was not exactly the same, but it was about the same. Quantum computing just totally blows that up. I once calculated that if you took all the silicon in Earth's crust and converted it into conventional computer chips and ran it for the age of the observable universe, the biggest number you could factor would be about 5,000 bits. And if you wanted to factor a 5,000 bit number on a quantum computer, that'd only take you about 2.5 hours if it was running at the same speed. So it's really a very dramatic thing. And besides factoring numbers, quantum computers can also be used for certain other things like simulating chemical reactions, which might help, for example, in designing new catalysts to generate cheaper energy or to design new medical drugs. But a question is, are quantum computers the end of the road? The natural next place to look is quantum field theory. Quantum field theory is the physics describing things where quantum mechanics and special relativity are both important. So quantum mechanics is important when you're describing small things like particles, and special relativity is important when you're describing fast things, things that are moving close to the speed of light. So in collaboration with Keith Lee and John Preskill, I've studied this question, and what we found was that conventional quantum computers can emulate quantum field computers. Anything that could happen with quantum field theory, you could simulate using conventional quantum computers. So this doesn't provide a new dramatic advantage in the way that quantum did over classical.
So what now?
Well, there is another aspect of modern physics that you could consider as well, namely general relativity. So this is Einstein's theory of space-time, his theory of gravity as being a curvature to space-time. And at present, it's not really well understood how to reconcile quantum mechanics with general relativity. A sufficiently small black hole would be a place in the universe where quantum mechanical effects and general relativistic effects would both be important. So if you had a black hole where general relativity and quantum mechanics both come into play, could we use that as some kind of hypercomputer? Does that give us something beyond what even quantum computers might give us? In recent work with Ning Bao and Adam Boland, I've started to investigate these models, just kind of looking at them one by one and saying, what would be the computational implications of these models? And in a lot of models, what you have to do to get general relativity and quantum mechanics to fit together is you have to modify quantum mechanics a little bit. And oftentimes, when you modify the postulates of quantum mechanics, all kinds of crazy stuff happens. You start to have signals being able to be transmitted faster than light. And if a signal is transmitted faster than light, then from a certain reference frame, a certain perspective, it's actually being transmitted backwards in time, which can lead to all kinds of crazy paradoxes. And a second thing that can happen is you get kind of insane computational power. So why think about these things now? We don't quite have the quantum computers ready yet to simulate quantum field theories. And as far as building computers out of black holes, that's very far from anything we can do today. And so today, we can look at imaginary computers of the far future. What powers will they have? And we hope that by thinking about this, we can not only push the limits of computation, but we can push the limits in terms of our knowledge of physics.